Why doesn't this stuff work? I need to figure out why. I'm going to try to record this now. So we're picking up in 8.3 with molecular orbital theory and hybrid orbital theory. These are two other bonding theories. The last one we talked about was Vesper theory, valence shell electron pair repulsion. And the idea behind that one is if you have two shared pairs of electrons that are making a covalent bond, those electrons take up space. The shared pairs take up more space than an unshared pair of electrons would. And so that dictates the shape that a molecule is in. So in other words, it explains when you have bonds, what shape do those bonds take in space. So these next two, molecular orbital theory and hybrid orbital theory, are a little bit about where the electrons go. So when two electrons are making a covalent bond, what are those electrons doing? And to make sense of this, we really need to go back and think some more about quantum mechanical theory. Okay, so if you remember, quantum mechanical theory said that electrons live in orbitals, and those orbitals have different shapes, right? So the most basic one is an s orbital that is a sphere, right? And so on the first principal energy level, you have one s orbital, right? You move up to the second principal energy level, and you have a 2s orbital, which is also a sphere, but then you also have p orbitals, right? So 2p stands for the second principal energy level, but then there are 3 of those orbitals, right? And they look like a pair of pairs, we said. Okay. So the idea here is that these shapes are the spaces that an electron can be found, right? So if the center of these shapes is the nucleus, right? And if we remember from what we read about, the nucleus is very tiny compared to the space that the electron cloud is in, then it could just be like this dot in the center, right? And these spherical shapes or pair shapes are shapes where you could find, at most 2 electrons each time. Okay, so that's quantum mechanical theory. Okay, so now in this theory, you're thinking about a single atom, right? And the electrons on that single atom. So when we learned about covalent bonding, we now say that electrons are going to be shared between 2 atoms. So essentially what's going to happen is these orbitals that we were introduced to in quantum mechanical theory, they have to overlap to form a bond. Okay, so let's now dive into molecular. Okay, so like I said, it draws on quantum mechanics, right? So we're thinking about the spaces that electrons can be found in. The first kind of bonding orbital is going to be called a sigma bonding orbital. So sigma bonds, so let's define sigma bonds first. They form between 2 s orbitals or p orbitals when those orbitals overlap symmetrically around the bond axis. Okay, so let's look at this picture here. Okay, so we've got this picture here. So we've got this picture of these 2 s orbitals. Okay, so let's say these are 2 hydrogen atoms. Okay, so we've got one hydrogen atom, and this is your second hydrogen atom. And we know that hydrogen comes together to make a hydrogen molecule, right? Those 2 hydrogen atoms can bond, okay, by sharing 2 electrons. So what's going to happen is that each of these s orbitals that has 1 electron in it is going to end up overlapping so that those electrons can be shared, right? So you go from having these 2 independent s orbitals to this one big bonding orbital that's called a sigma bonding orbital. Okay, so when 2 s orbitals or 2 p orbitals, I'll show you what that looks like in a second, overlap, they create a sigma bonding molecular orbital, which is essentially a single bond. Okay, so a single bond is made with a sigma bonding orbital. Right, so let's now look at what a p might look like. Okay, so we know that the p orbitals are shaped like this, right? So let's imagine that you have, let's say that we have 2 fluorine atoms, right? So fluorine has enough electrons that their outermost electrons are going to be in a p orbital, not in an s orbital. So when those 2 fluorine atoms create a bond, what's going to have to happen is your p orbitals are going to come together, okay, and overlap, and they're going to create one big bonding orbital, which as we now know is called a sigma bonding orbital, right? And they have these funny little shapes on the end, right? Which is this side that did not quite overlap, right? So this is what a sigma bonding orbital looks like when it's made between two p orbitals. Okay. So that's a sigma bond and a sigma bonding orbital according to molecular orbital theory. Okay, you cannot mix and match, by the way, the overlap of s orbitals and p orbitals. Okay, so either the two bonding orbitals have to be s's or they have to be p's. Okay, now that explains single bonds. Now, pi bonds are going to help us understand double and triple bonds. Okay, so a pi bond is defined as a bond where the orbitals overlap on either side of the bond axis. Okay, two p orbitals might overlap above and below the bonding axis. What's the bonding axis, first of all? Okay, so once again, let's talk about some. Now we'll talk about oxygen now. Okay, so you've got an oxygen atom here. That's its nucleus, right? And that's one of its p orbitals. Okay, I'm right now drawing the bonding axis. Okay, so here is your other oxygen atom with its nucleus and its p orbital. Okay, so these are the two atoms that are going to be bonded together, right? And the bond axis is the straightest line in between the nucleus of the two atoms. Okay, that's the bonding axis. So if the orbitals overlap above and below the bond axis, they end up creating a shape that looks like this. So you're going to have like this little cloud above and this cloud below, okay? And your nuclei are here like in between those two clouds, right? So even though this is two distinct shapes, this is a single pi bond, all right? And this is a single pi molecular orbital, okay? Now, what it says here at the bottom is that a sigma and a pi bond together can make a double covalent bond. What might that look like? Okay. Okay, we're gonna,